I invite Senthil to give his final lecture in this lecture series. I'd like to say a few things. So, first of all, I'd like to thank Senthil for coming and giving these fabulous talks. The first two talks have been excellent. I'm sure this one will be as well. So, we're very grateful to him for doing that despite a difficult personal situation. Thank you very much. I'd also like to thank Professor Vadia and ICTS for all the support and encouragement and generosity in terms of funding, which made the program possible. Thanks to all the speakers who've come from various parts of the world and different parts of the country. I think we've been very fortunate to have so many experts in so many different branches of condensed matter physics at this meeting. It certainly made it, the discussion meeting and also all the interactions wonderful. I'd like to thank all of you, all the participants, for asking questions and engaging in lively discussions during the breaks and during lunch. So that's been great as well. I'd like to especially thank those who are outstation participants, mainly for their patience and understanding in putting up with some inconveniences related to housing and internet access. We are very sorry about that, and thanks once again for understanding. Also thanks to my colleagues from the physics department and the Center for High Energy Physics, who were very cooperative and let us use different facilities of this building, like the auditorium and the dining area and the parking lot. And finally, I'd like to say that all the credit for the smooth conduct of this program should really go to the wonderful ICTS administrative staff. They're unfortunately not here right now, but I would like to mention them by name. So there's Mukesh, there's Parul, there's Jiva, Rubina, Manasi, Mayank, and I don't know, maybe I'm forgetting a couple of people. But even though they're not here, I'd really appreciate it if all of you could give them a big hand for all the effort that they've put in. And thank you once again. And so now let me invite Senthil to deliver the final lecture.
And while we're thanking people, I think it's appropriate to thank Shubroto and Kedar for all the hard work that they put in. I don't need the mic, I guess. So it's been wonderful for me to be here this week and give these lectures. I've certainly been very stimulated both by the questions that people have been asking and by the other talks that I've listened to. So the first lecture was an overview of things that have gone on in the field in the last 20 years or so. The second lecture was on very recent work that we completed, but which we will hopefully write a paper on at some point. But today I wanted to sort of bring you up to a stage where I can explain to you some work that I'm currently doing and which I've not yet completed. Right? I was joking with some of my friends that I had to do the work last night so that I could talk about it today, but the banquet meant that I couldn't complete it. That's the only reason. All right, so the work that I'm going to talk about is on the metal-insulator transition, a class of metal-insulator transitions known as the Mott transition. So most of the work will be on older stuff. Most of the talk will be on older stuff, which builds up to the project that I'm currently engaged in. And it goes back at several years to papers that are written with a bunch of people, Daniel Podolsky in Israel, Arun Paramakanti, and Jungbaek Kim in Toronto, David Ross, a former student, Drew Potter, also a former student, Mason Berkeshli, John McGreevy, William Vichak-Krempa, and Puyan Gaemi. Okay. So let me start with some motivation. At least that's what motivated me for this project. So it's the phase diagram of the cuprates. So Joel Moore showed a wonderful phase diagram which showed up in a talk given by his collaborator and colleague, Joe Orenstein, a few months back at my home institution. And Orenstein characterized that same phase diagram. He looked at it and said, obviously this phase diagram was drawn by a committee. Okay? Because all kinds of people have all kinds of opinions, so you put everything. So this is a phase diagram that I drew by hand. So clearly it's meant to be schematic. It's a phase diagram of the cuprates. Q-plate is still one of the most fascinating problems in quantum condensed matter physics after more than 25 years. So presumably everyone has seen this phase diagram before, or most of it at least. So one of the things that's been getting a lot of attention in the last couple of years is this dome associated with what's known as charge order. So it's a breaking of translation symmetry that's been seen in a variety of probes, most strikingly in X-ray experiments. So this is there. This is the latest addition to the phase diagram. But the biggest mystery, at least to me, in the Q-plate phase diagram is this region known as the strange metal. Okay? And this talk is sort of motivated by the existence of the strange metal. Okay? So, over the years, there have been many, many ideas on the strange metal, but with time, it seems as though there's some set of ideas that look more plausible than others. And one idea that goes back a long time, many, many years, is that the strange metal is plausibly linked to quantum criticality of some kind. So there's increasing evidence in the phase diagram for something special happening at a critical doping of about 19%. Okay? So this was suggested, I guess, about 15 years back through an analysis of thermodynamic and transport experiments by Talon and Lorem. So they pointed out that it appears from a variety of experiments that the famous pseudo-gap crossover, which occurred at some finite temperature in the underdoped samples, terminates, if you extrapolate it, it terminates, that crossover terminates at 0 temperature at a critical doping of about 19%. And in the years since, this seems like a not crazy thing to say. It seems like it may actually be a reasonably correct statement. More recently, this charge order that I've indicated here, there have been experiments trying to see at what doping, as you decrease the doping, at what doping this charge order first onsets. And in a Tour de Force recent paper by Bernard Keimer's group, they argued reasonably convincingly that the onset of charge order also happens at the same magical doping. Okay? So it appears as though there is something special about that doping level, 19%. And so plausibly, the ground state of the underlying normal ground state at this 19% doping is something that controls the behavior of the strange metal region. The fluctuations, the excitation structure of the normal ground state at this special doping plausibly control the behavior of this region. Okay? So that's an idea that I think is a reasonable idea to pursue. Time will tell whether it's the right idea or not. So there's some properties of the strange metal that some of which have been indicated by a variety of experiments for, again, decades, some more recent. So what we know is that in the strange metal region, it appears as though there is a sharp Fermi surface where gapless electronic excitations reside. But it also appears that these excitations do not take the form of Landau quasiparticles. So it looks as though we have a sharp Fermi surface, but no quasiparticles. Okay? Now, because the charge order onsets around the doping level where you first see where the strange metal exists, it's quite natural to presume that there are also critical charge order correlations in the strange metal, though experimentally there's no direct evidence for this at all at this stage. But logic, would suggest that if there is, if 19% is where this, the charge ordering onsets through a second order transition, that around the doping level you should have critical charge order correlations. Okay? So in other words, we imagine that the critical degrees of freedom at whatever quantum critical fixed point controls the strange metal, that those critical degrees of freedom should include non-Fermi liquid electronic excitations at a sharp Fermi surface and critical charge density wave fluctuations. Okay? So these presumably are minimal ingredients that go into, this is the degrees of freedom that go into the description whatever description exists in the future of the strange metal fixed point. Okay, so my motivation for this project was a very, very lowly theoretical challenge motivated by this phenomenology. Can we construct examples of such strange metal fixed points at finite density where there is a gapless Fermi surface but no Landau quasi-particles coexisting with critical charge order correlations? Okay? So it's an exercise in theoretical physics, right? And you do this and then see what one has learned. Okay? All right, so that's the project. Okay? It's an ongoing project. And I'll tell you how much I've been able to do in this direction so far. So I'm going to take a route to constructing some examples of this kind by focusing on commensurate density. X is maybe a quarter or maybe 1/5. Actually, the initial spark for this project was the recognition that 19 is close to 20. Right? So 19% is close to 20%, and 20 is a simple rational fraction. It's 20%, it's 1/5. Okay? I don't take that very seriously, but it was it did help. So let's focus on commensurate density and ask the question whether there are continuous Mott transitions from a Fermi liquid to a Mott insulator at these commensurate densities. So if one could describe such a continuous phase transition, then the corresponding critical fixed point one might expect will be a strange metal with what one may call a critical Fermi surface, where there's a Fermi surface but no Landau quasi-particles, and quite naturally you might expect that it would coexist with critical charge order correlations. Okay? So let's see whether this gives an example or not. So the plan of the talk is the following. I'll first review older work from a few years back that I did on a theory of a continuous Mott metal insulator transition in 2 dimensions at 0 doping, namely at half filling. Turns out this theory is very interesting for its own sake. Helps us address many difficult questions about this kind of phase transition and makes some very definitive predictions for experiments. And then I'll turn my attention to Mott transitions at commensurate filling. Actually, the filling will be 1 minus 1/q, that's a typo. I'll set up a framework to a formulation. I'll provide a formulation of this transition and take some initial steps towards doing something with that formulation by warming up, by studying by reviewing the results on a simpler problem of the superfluid insulator transition of bosons at commensurate filling. Okay? And so the talk will end somewhere halfway because that's all I know so far. Right? But I think what I know so far, there are interesting things there, and there are definite projects for people to do based on that. Okay? Okay, so let me start with the first topic, continuous Mott metal insulator transitions in 2 dimensions at half filling. So the electronic Mott transition is one of those ancient problems in the field that has never been solved. So the question is, how does a metal evolve into a Mott insulator? So as a prototypical model to address this kind of question, one may want to write down, say, a 1-band Hubbard model at half filling, and so as to not deal with complications associated with Fermi surface nesting, it's convenient to study this problem on a non-bipartite lattice, for instance, on a triangular lattice. And so let's see what happens in this model. So the Hubbard model is characterized by 2 parameters, T and U. So it's 1 dimensionless parameter, T over U. If T over U is big and you're on a non-bipartite lattice, the ground state will be a Fermi liquid with a full Fermi surface, which corresponding to the density of electrons per unit cell. If T over U is small, you will get a Mott insulator, and this Mott insulator will have spin exchange. And even on a triangular lattice, it goes into an antiferromagnetic ordered state. So you get an antiferromagnetic insulator, and of course the insulator has no Fermi surface. And the question about the Mott transition is how to evolve between these 2 extremes. So why is this been such a hard problem? Right? So first, Arindam today, I don't know if he's around, there he is. He was posing this question of what's the order parameter for the metal insulator transition. And I think the right statement to make is that that's the wrong question to ask. Order parameters capture Landau ordering, right? Neither the metal nor the insulator is correctly described in terms of a broken symmetry alone, right? So, there are things that have order parameters and there are things that don't, and we can't force things that don't have order parameters to have one, right? There's no order parameter for the quantum Hall effect, for instance, or for a quantum spin liquid, right? So there is no order, but the absence of the order parameter means that some of the standard methodology that we have for discussing phase transitions, which is to focus on long wavelength, long time fluctuations of the order parameter, necessarily, we have to give up on those because there's no order parameter, right? More fundamentally, we have to deal with the existence of the gapless Fermi surface on the metallic side. So it's clearly not just a theory of some fluctuating boson field, but you also have gapless fermions in the problem, and there's a full Fermi surface worth of excitations. Finally, there's a complicated interplay between the fundamental phenomenon of the metal-insulator transition and the other phenomenon of the magnetic phase transition, right? So all of these make life difficult in studying the mode transition. And furthermore, typically in most materials, the mode transition is actually first order. And if something is first order, what are you going to say, right? Other than that, it's first order. But despite it being first order, in many, at least in some frustrated lattices, the transition is sometimes only weakly first order, and you do see fluctuation effects that are visible as you approach the mode insulator from the metal. Okay? So it's not just a strong first order transition, it's weak first order, so it looks like it may try to be a second order transition, and you see various phenomena that you attribute to the impending mode localization, but it's not quite a second order transition. So how do you deal with these kinds of things? So we don't know, and that's why the problem has remained open and central to a large number of phenomena in the field. So what I'm going to talk about today, we now know, as I described in my previous lectures, there's a class of mode insulator that does not have any magnetic long-range order, namely these quantum spin liquid mode insulators. So these provide us with an opportunity to make progress on the mode transition, on the phenomenon of the metal insulator transition, without the complications of magnetic long-range order, right? So at least one of the things that complicate the study of the mode transition, we might have hoped that it's gone for this class of phase transition. So there's many candidate spin liquid materials, as I described in my first talk. There's these two organic spin liquids, which are in 2 dimensions. There's this 3-dimensional hyper-Kagome lattice system that Yogesh Singh, wherever he is, has been studying in his experiments and has been synthesizing. And there are also these 2D Kagome lattice systems, Herbert-Smithite and Volbothite. Now there's a difference between these two classes of, between these various spin liquids. The first set of examples all seem empirically to be close to pressure-driven mode transitions. They're very close to the metal insulator transition, while these Kagome examples are what one may call strong mode insulators. They're very, very far away from the metal insulator transition, and so clearly, theoretically, one has to think about these two classes differently. Okay? So all the candidate spin liquid materials so far empirically seem to have gapless excitations, at least at temperatures well below J. We, of course, never know whether it's a strictly zero temperature property or not. And this has been most extensively studied in these organic spin liquids with J on the order of 250 Kelvin, and they seem to be gapless down to at least 200 millikelvin. As an example, in this DMIT material, I already showed this data on, in my very first talk. Even though it's an electrical insulator, the thermal conductivity divided by temperature extrapolates to a constant at 0 temperature. So it's thermally, it conducts heat like a metal, even though it conducts electricity like an insulator, right? So what this means is that this organic material, which is very close to the mode transition, has managed to retain some aspects of the metal, at least as far as heat transport is concerned, even though as far as electrical transport is concerned, it's an insulator. Okay? And there's a possible experimental realization of a second order mode transition in these organics, in one of the organics, kappa ET. So as a function of pressure, it goes from a Mott insulator to a metal, quite likely a Fermi liquid, through a transition which, if at all its first order, is only very weakly first order. Okay? There's a small blip of superconductivity here, below 3.5 Kelvin, but on the big energy scale that characterizes this phase diagram, this is a tiny, tiny region which we won't focus on. Okay, so let's think about the possibility of a Mott transition to a quantum spin liquid from a Fermi liquid. So some fundamental questions are, can the Mott transition be continuous? What happens to the electronic Fermi surface? So again, returning to this phase diagram, as function of T over U, let's say on the triangular lattice, as is appropriate for the organics, large T over U have a Fermi liquid state with a full Fermi surface. At intermediate T over U, when the system has just become a Mott insulator, on the triangular lattice, there's actually a lot of evidence, both from experiments and theory, that you go into a spin liquid Mott insulator. But any insulator, whether it's spin liquid or not, has no electronic Fermi surface. So something needs to happen to the Fermi surface along the way. So if you start thinking about this problem, you realize that conceptually, the Mott transition is very, very weird. Right? So let's, even to the spin liquid. So let's see why. Now let's decrease T over U while staying in the Fermi liquid side and ask what happens. Now the Fermi surface needs to disappear somewhere when the system, along the way, when the system becomes an insulator. Right? So let's ask how this disappearance of the Fermi surface happens. Okay? But we know that since this entire system is at half filling, it's the same density throughout, that throughout the metallic phase, the size of the Fermi surface is fixed completely. Right? There's a theorem, this Schrodinger's theorem, that tells you that the size of the Fermi surface is set by the number of electrons in the unit cell. And we're not changing the number of electrons in the unit cell, therefore the Fermi surface maintains its size throughout the Fermi liquid phase. So the Fermi surface has to disappear when you go into the insulator, but it can't disappear by shrinking and reducing to 0. Okay? It has to disappear while maintaining its size. Okay? So this means that as we approach the Mott insulator, the entire Fermi surface must die while maintaining its size, right? Which is a very, very bizarre phenomenon. Right? For instance, if you go from a metal to a band insulator by changing the doping, the size of the Fermi surface will just decrease continuously to 0. Right? But to a Mott insulator, it's not allowed to do that because of Schrodinger's theorem. So if the Mott transition is second order, the critical point is necessarily very, very unusual, and something very bizarre needs to happen. Okay? So the Fermi surface will be on the brink of disappearing right at that putative critical point. Okay? So clearly we should expect non-Fermi liquid physics in some very striking manner at such a phase transition if it is continuous. Okay? So this kind of killing of the Fermi surface apparently also happens in heavy fermion metals and perhaps also happens in the cuprates, but I won't talk about any of that, at least not heavy fermions here. Okay, so the crucial conceptual question is, how can this at all happen? How can a full Fermi surface disappear continuously while maintaining its size? Okay? So it's an old idea that goes back, I guess, 44 years. It's due to Brinkman and Rice. And the idea is the following. So if you look at the momentum distribution in the ground state, in a Fermi liquid, there's a jump discontinuity at Kf. And the size of the discontinuity is this quasi-particle weight, the residue associated with the quasi-particle pole, the electron Green's function. Now in an insulator, there is no Fermi surface, and this N of k is smooth. So how do you go from here to there continuously? Right? So if you pose the question this way, the answer is obvious. What needs to happen is that this jump discontinuity in N of k has to go to 0 continuously. Okay? So that's the essence of the Brinkman-Rice proposal. At least a part of the Brinkman-Rice proposal. And by now, there's actually concrete examples of this kind of continuously vanishing Z, both from DMFT calculations in infinite dimension and from various things that Subir and I have done in 2 or 3 dimensions based on slave particle theories. So the basic question for theory then is, so okay, maybe this is how the Mott transition happens, but then what happens right at the critical point? What's the nature of the electronic excitation right at the quantum critical point when Z has just become 0. Okay? So the claim that I'm going to now try and justify to you is that at the critical point, the Fermi surface remains sharply defined even though there's no Landau quasi-particle. Now, we know that there's no Landau quasi-particle because Z, which characterizes the weight of the Landau quasi-particle, has just gone to 0. So once Z is 0, there's no Landau quasi-particle. Okay? So the non-trivial statement here is that even though there's no Landau quasi-particle, the Fermi surface remains sharply defined. Okay? And this is what I'll call a critical Fermi surface. So let me now argue for that. Let's restrict to 2D, though everything I'm saying will also hold since I see string theory, it's even in 10 dimensions. Sorry. There'll be some kink, right? There'll be some singularity. May not be a jump discontinuity in the derivative. So let's ask the following question. Let's ask about the gap delta of k to add an electron at momentum k in the Brillouin zone to the system. Okay? Now in the Fermi liquid, this gap is 0 all along the Fermi surface. That defines the Fermi surface in the Fermi liquid. While in the Metal-insulator, there's a sharp gap delta of k, which is non-zero for all k. There'll be a sharp threshold to add single particle excitations at any given momentum k. Now beyond the threshold, we don't know what the behavior is, but there will be a sharp threshold. No. Here there is a Fermi liquid, right? There's a Fermi liquid here, there's a Metal-insulator here. I'm now going to talk about the critical point. But these two statements are about either the Fermi liquid or the Metal-insulator. Okay? Right. So now as I approach the mode transition from, say, the insulating side, the mode gap, the single particle gap, has to go to 0 if the transition is continuous, because the Fermi liquid doesn't have a single particle gap. So the question is, how does that happen? So if the mode transition is second order, delta of k has to close continuously. But to match the Fermi surface in the metal, I require that delta of k go to 0 for all k that belongs to the Fermi surface. Right? So the place where the gap closes in momentum space must match on to the Fermi surface of the metal on the other side. Okay? This means the Fermi surface is still a privileged surface right at the critical point. So the Fermi surface is a sharply defined surface at the critical point. But Z is 0, so there's no sharp quasi-particle. Consequently, right at the mode transition, I'll have a non-Fermi liquid with a sharp critical Fermi surface. Okay? So that's the argument. So another way to think about it is, as Vijay was asking, in the metal with the Fermi surface, n of k has this jump discontinuity, which is Z. In the Metal-insulator, where the Fermi surface disappeared, n of k is some smooth function of k. Now, right at the critical point, you expect something intermediate between these two behaviors. So you expect, and if the transition is continuous, you expect that n of k has a singularity, is continuous, but has some other singularity at kf. Okay? And the location of the singularity will then determine the location of this critical Fermi surface. Okay? So let's return to these questions. Can the mode transition be continuous, and what's the fate of the electronic Fermi surface? So currently, as far as I know, and as far as anyone knows, there's only one available theoretical framework to answer these questions. Okay? And that's slave particle gauge theory, of the kind that I described in my first lecture, and I'll talk about it more now. And a mean field theory for this kind of mode transition was proposed, I guess, nearly 10 years back by Florence and George. And the spin liquid phase itself was described along these lines by Leszek Motrynich, who's in the room, and Sungsek and Patrick Lee. So the idea in the slave particle framework is to split the electron operator as a product of a boson and a fermion, with the boson carrying the electric charge, but not the spinostatistics, and the fermion carrying the rest. So this boson is either called a charge-on or hole-on in the literature. F is usually called the spin-on. So in this description, what you do is to imagine that F has formed a Fermi surface. Right? F is a fermion, so you imagine that F has formed a Fermi surface. And then the fate of the system is determined by what B is doing. if B condenses, if B forms a superfluid, you can argue that that's just a Fermi liquid, because if B condenses, then the C and F are indistinguishable from each other. They differ just by a complex number. And F has formed a Fermi surface, and so C forms a Fermi surface. So that's the description of the Fermi liquid in this framework. Now in the Morton-Slater, on the other hand, B is gapped. Okay? You assert that B is gapped, that B has formed a bosonic Morton-Slater, and then the electron, the spectral function will also be gapped, and so you get a Morton-Slater. So this framework then gives a very natural description of a possible Fermi liquid to Morton-Slater transition. Of course, the Morton-Slater turns out to be exotic, and it turns out to be a quantum spin liquid with an emergent Fermi surface of neutral excitations. So then, right at the critical point, naturally, what you would expect is that this B field is critical, right? So in this description, you describe the electronic mode transition by first going to these slave particle variables, letting F form a Fermi surface, and then associating the electronic mode transition with the superfluid insulator transition of these emergent bosonic particles. Okay? The low energy effective theory consists of coupling both this B and F to a fluctuating U1 gauge field, and this gauge field comes about because of redundancy in this representation. Okay? And I already showed you this picture. The picture to keep in mind is that the description of the metal is as a static ion cores, positively charged ion cores, with provide a background on which there is a sea of negatively charged electrons that are swimming around. The picture of the Morton-Slater is that the electric charge of these ion cores has been neutralized by binding just the negative charge from these electrons to these ion cores to form neutral entities, while the spin and statistics of the electrons stay as mobile itinerant objects that form a Fermi surface. Okay? So can the mode transition be continuous, and what's the fate of the electronic Fermi surface? Now it turns out that based on the slave particle framework and analyzing fluctuations, several years back I was able to develop a concrete and tractable theory for a continuous mode transition from a Fermi liquid to a quantum spin liquid. And this theory was tractable enough that one could demonstrate the emergence of this critical Fermi surface at the mode transition. And it leads to a number of definite predictions for many different quantities. I won't describe all of them. I'll describe some of them in the next few slides. But let me just list some of the predictions. One prediction which is probably very pertinent to experiments is that you're going from a metal to an insulator, right? So what happens to transport? So what this theory leads to is a prediction that as you approach the transition from the metal, that the residual resistivity will show a universal jump of order h over e squared. Right? And in a few slides, I'll show you an estimate of this universal jump of the residual resistivity. Another prediction is that the quasi-particle effective mass in the Fermi liquid will diverge as you approach the mode transition, but will diverge very weakly, only logarithmically. A third prediction is that unlike a usual kind of quantum phase transition, there's more than one diverging time or length scale at this mode transition. There's two diverging time or length scales, one associated with charge fluctuations, the other associated with spin fluctuations. Okay? And finally, it turns out that the intermediate length scale between these two length scales, or intermediate time scale between these two diverging time scales, there's an emergence of a kind of state that had been postulated phenomenologically for a number of years, known as the marginal Fermi liquid. That state emerges very naturally as an intermediate scale, as a description of the intermediate scale physics near this mode transition. Okay? So the picture of this finite temperature crossovers near this continuous mode transition looks like this. So many of you have grown up reading Subir's book on quantum phase transitions. So you all know the famous diagram that, Kedar and I certainly grew up drawing that diagram. Every page of our research notes from those days has Subir's famous diagram of finite temperature on this axis, some tuning parameter on this axis, and a fan. So it's this so-called quantum critical region. So the analogous diagram for the electronic mode transition is different. There's two crossovers. There's a if you're sitting right at the critical point and you go up in temperature, there's a quantum critical non-Fermi liquid. And then you ask, how does this cross over into the Landau-Fermi liquid if you're on the metallic side of the phase transition? And as I said, it turns out that the crossover out to the quantum critical non-Fermi liquid is not directly the Landau-Fermi liquid. Rather, it first crosses over into a marginal Fermi liquid metal. It's called a marginal Fermi liquid because of the structure of the electron Green's function, which is precisely of a kind that was proposed phenomenologically many, many years back by Chandravarma and collaborators. So it's a marginal Fermi liquid. And then eventually, at a parametrically lower scale, this marginal Fermi liquid gives way through a second crossover to the Landau-Fermi liquid. And loosely speaking, this is the scale at which the charge fluctuations realize they're no longer critical, and this is the scale at which the spin fluctuations realize that they're no longer critical. Okay? I know, Subir. But most of the book has only one. Yeah. All right. So where do these results come from? So let me give you some feel for it because that's important for my ongoing current project. Okay? So the field theory for the critical point, I already argued, you must take this boson field and couple it to a fluctuating U1 gauge field. And this boson is undergoing a superfluid Metal-insulator transition at a filling of 1. Right? While the fermion has formed a Fermi surface, and it's also coupled to the same gauge field, A. Now, there are many steps in the logic that enable us to actually solve this problem. And the first thing is to recognize that because of the coupling to the Fermi surface, there's a phenomenon known as Landau damping of the gauge fluctuations. What this Landau damping means is that the effective action for the transverse portion of the gauge field, usually we don't need to worry about the longitudinal portion of the gauge field in a problem like this. It's screened by the Fermi surface. So the transverse gauge field has a term which for imaginary frequency looks like mod omega over q. Now, the presence of this kind of Landau damping, which comes from the Fermi surface, means that this gauge field essentially dynamically decouples from the critical boson fluctuations near the mode transition. And the reason is that the critical boson fluctuations are described by a 2 + 1 dimensional XY model, right? Because it's a superfluid insulator transition of bosons at integer filling. And since, of course, all of you have read Subir's book, you know that that's described by a relativistic quantum field, a relativistic conformal field theory. That is the 2 + 1D XY model. Now, this model, since it's relativistic, its important critical fluctuations occur at frequencies of order the momentum. On that scale, this looks like a mass term, and this is the rough argument, and therefore, these gauge fluctuations don't affect the bosonic criticality. Okay? But the weird thing, so that's the first observation. The second observation is that even though the bosonic criticality is not affected by the gauge fields in themselves are affected by the bosonic criticality. Right? It's a one-way effect. Right? And the reason is the following. The effective gauge dynamics, so this term, this Landau damping, comes from the Fermi surface fluctuations, while the critical boson fluctuations lead to a term in the gauge dynamics which looks like this. This is the standard response of a relativistic quantum critical fixed point to an external gauge field, and it merely reflects, if you wish, from the fact that a 2 + 1 dimensional superfluid insulator transition of bosons is characterized by universal conductivity that's of order 1 at the critical point. Or equivalently, or more formally, you can say that it's fixed by the scaling dimension of the vector potential at this CFT, and the scaling dimension is fixed to be 1, and therefore scaling determines the structure. So we have some effective action of this kind, and anticipating that but as far as the fermions are concerned, that the kinematic regime that's relevant is frequency much smaller than q, we can ignore this omega squared in this term and end up with this effective action for the gauge field, which is modified from what it would have been had the bosons not been critical. Had the bosons not been critical, this would have been a q squared, would have been analytic in q. Right? Now, with this form of the gauge dynamics, the typical frequency scale for the gauge field is of order q squared. So this is what we call a Landau-damped gauge field with a dynamical exponent of 2. Now it turns out, so the spin-on Fermi surface is coupled to such a gauge field. And these problems of Fermi surface coupled to a gauge field have been discussed in literature for a long, long time. It's still ongoing discussions, but one limit in which the problem is actually understood is when the gauge field is precisely such the dynamical exponent equal to 2 dynamics. Okay? This turns out to be a tractable case where the coupling to the gauge field only introduces marginal deviations from Fermi liquid behavior. Okay? So the final effective critical action has at 0 temperature has the critical 2 plus 1 dimensional XY model and for the charge sector, and for the spin sector it has the spin-on Fermi surface coupled to this Landau-damped gauge field with dynamical exponent 2, and both of these theories are individually understood, and so then we can put it together and develop a theory of the full electronic mode transition. Okay? So there's many steps in the logic and it's a bit complicated, but it seems to work. Okay? So there is one twist to this nice sounding story. I don't know if it's nice sounding, I have lover's eyes. There's a twist to the story which we realized only a few years back, only 2 years or so ago. If you're interested in non-zero temperature transport or dynamics, as we should be, if we want to say go ahead in experiments and look for this prediction of this universal jump with the residual resistivity or things of that sort, then we have to deal with this, revisit the logic that I just described at non-zero temperature, and then all these frequencies become Matsubara frequencies. And then there's a curious phenomenon. There's a zero frequency, there's zero Matsubara frequency fluctuation, which are the static gauge fluctuations, which are not Landau-damped. Right? The Landau damping is not effective at 0 Matsubara frequency. So those static gauge fluctuations survive at non-zero temperature, and they do not decouple from the critical bosons. So the gauge fluctuations decouple from the critical bosons because of Landau damping, but at non-zero temperature, there's static gauge fluctuations that don't decouple, that are not Landau damped, and we have to take them into account. And what this leads to is an extra scattering mechanism for the bosons, which is not there at the usual superfluid insulator transition of bosons in 2 plus 1 dimensions. And clearly, we should expect that this will affect transport. And indeed, you can try to calculate the conductivity of these critical bosons by including the scattering from static gauge fluctuations at non-zero temperature. So these problems of calculating transport of quantum critical bosons have been going on for a long time, have been discussed for a long time. There's pioneering work in this area by I just did, but put it back into my pocket. Maybe leave it here. So pioneering work by Kedar Damle and Subir Sachdev from when Kedar was a graduate student, he is, which I was witness to as his office mate, calculated the universal conductivity of precisely this transition is 2 plus 1 dimensional XY quantum critical point in a suitable large N approximation way back in 1997. And Subir has continued to think about that for, I guess, 2 decades now. But here, we can build on the theoretical technology that Kedar and Subir developed and include this extra scattering mechanism and calculate the universal conductivity while including this. And it turns out that what it does is to reduce, not surprisingly, it reduces the universal conductivity because of extra scattering. And at least in the large N approximation, it reduces it by about a factor of 8. So this reduction of the universal conductivity is, I don't know if the number 8 should be trusted in general, but the qualitative phenomenon is that there's a reduction of the universal conductivity compared to the problem without the gauge field. So this actually enters experimental quantities. At the electronic mode transition in this kind of slave particle theory, it's been known for a long time that the correct way to calculate the resistivity is to add together the resistivities of the boson and fermion. This is a rule going back to Ioffe and Larkin. So the reason there's a universal resistivity jump is that the fermion resistivity is not doing much across the phase transition, while the boson resistivity goes from 0 in the metallic phase, where the boson is superfluid, to infinity in the insulator, where the boson is an insulator. But right at the critical point, this is non-zero and is a universal constant. So consequently, as you approach the transition from the metallic side, this rho b jumps from 0 to a universal constant, and so experimentally it will show up as a jump of the residual resistivity by a universal constant. Since what jumps is the residual resistivity, and what's reduced is the conductivity by a factor of 8, this means that the universal resistivity jump is enhanced from whatever answer Kedar and Subir found by a factor of 8, right? By some factor which turns out to be 8 in the log n limit, right? So this is so the direction is good. So in principle, if somebody did an experiment measuring this universal resistivity jump, they should see a jump that's at least as big as the universal resistivity of the superconductor insulator transition, maybe multiplied by factors of 4. But they should see a bigger jump than what you expect for the superfluid insulator transition of bosons. So the kind of experiment that one would do is to look at this kind of mode transition, perhaps in the organics, and take various cuts through this phase diagram at various doping levels, and then plot the resistivity as function of temperature along each one of these cuts. In the insulator, you should see this insulating resistivity. On the metallic side, you should see a resistivity that flattens out to 0. But then, very close to the transition, this residual resistivity will jump by some number of order h over e squared that we've estimated in this log n calculation. Okay? There's a number of other things that we could say about the transition, the various crossovers and exponents and so on. All of that are known. I wish I could tell you that all of these predictions have been verified beautifully in experiment. Unfortunately, I can't. There are experiments that are underway in the CUP-IET class of organics. The preliminary data looks suggestive, but it's only suggestive. It's not at a stage where we can declare victory yet. Right? Yeah. Sorry? Yeah, and some of, obviously the XY model, there's an OG study of that that's 40 years old. Sorry? No, so the one thing that I should say is that though I haven't emphasized it, the OG point of view totally informs all the discussion. Right? Oh, there's no equation. Yeah, you won't find very many. Actually, this talk has many, many more equations than I normally put in a talk. And I was going to apologize for it being too equation heavy. All right. I mean, there's a lot of equations in the papers, but yeah. All right. There's no superconductivity in the model. In the experiment, there is this tiny blip of superconductivity, which also complicates trying to measure this very carefully. At low temperature, there's many, many problems with the experiment. Because it's under pressure, the pressure is not homogeneous inside the medium. And so because in homogeneous strain, the resistivity at low temperature has all kinds of jumps. Of course, I want resistivity to jump, but it's clear that some of it is due to inhomogeneous strain. And anyway, the experiments are underway both in CUP-IET and in DMIT, but given this time scale for organic experiments, it's probably going to take a long time. That field moves very slowly. Okay, so that's all older stuff, but it gives the background for my current project, what I'm going to talk about now. I want to talk about a generalization of this theory to the electronic mode transition at filling 1 minus 1 over q. Sorry about the typo. I want to give you a formulation of that. Okay, so now I want to come back to the square lattice because I'm thinking about cuprates. And once I'm away from half filling, there's no nesting or anything that I need to worry about. So I want to think about the mode transition at commensurate filling on a square lattice. I want to consider filling 1 minus 1 over q. And in principle, I can drive a transition from a uniform Fermi liquid to a translation broken Metal-insulator. I necessarily need to break translation. I actually don't necessarily need to, but typically I will need to break translations to get a Metal-insulator at this filling because not enough electrons to fill up all the lattice sites. And again, not being very imaginative, I'll just try to repeat the success of half filling by using a slave boson approach. So let's try to use the slave particle approach, write C alpha as B dagger times F alpha. So then the boson is at filling x equals 1 over q, and the fermion is at filling 1 minus x. As before, if the boson condenses, I can form a uniform Bose condensate, and that will be, and F forms a Fermi surface. That will yield a Fermi liquid at this density. And as before, to get a Metal-insulator, I must put my boson in a bosonic Metal-insulator. Now, so long as q is bigger than 1, so I'm at some commensurate filling, but it's not at the filling at which the bosons can form a nice translation invariant insulator. This insulator will typically break translation symmetry. Okay? So this kind of mode transition addressed within this framework will give me a transition from a uniform Fermi liquid to a translation broken Metal-insulator. Okay? So in this framework, the slave boson once again undergoes a superfluid to insulator transition, but it's now a superfluid to charge ordered insulator transition at some non-zero density. Okay? Now, what do we know about such a phase transition? Now, since many of us have spent many years of our life doing all kinds of weird things, we know that this transition may actually be second order. Okay? And that's the deconfined quantum critical point that Ribot described in his talk. Okay? Ribot actually studied towards the end of his talk, he studied the case of q equals 2, and he argued that the transition was probably first order. But it could have been second order, right? No, in the sense that it's a fluctuation-driven effect. It's a mean field level. It's second order. Okay? So to illustrate the point, I'm anyway not interested in q equals 2. I'm interested in q equals 4 or q equals 5. At q equals 2, one insulator that you could get is a period 2 stripe, where the bosons sit at the bond centers. It's a so-called bond-centered stripe. So this is both, it breaks both lattice translation symmetry and breaks lattice rotation symmetry. It has both stripe order, translation breaking, and rotation breaking, so-called nematic order. Okay? Now we know that the superfluid to Metal-insulator, to this kind of Metal-insulator transition at q equals 2, it's a complicated problem, right? Naive intuition would say that it's obviously not second order, but then based on this theory of deconfined criticality, we know that it could have been second order, and there was a field theory that was proposed for it. And now, based on what Ribot told us 2 days back, we think that it's probably not second order. So it sort of has a complicated history. It doesn't have an obvious answer, right? So I want to think about higher q equals 4 and so on, where the answer is not at all obvious, right? So the main point is that this transition could have been second order, this kind of transition. Even though both phases break two completely different symmetries, neither of them is exotic, at least in the boson sector, but nevertheless, the transition could have been second order. Right? That's a highly non-trivial statement. The fact that it requires Ribot's extensive numerics to show that it's not second order is itself a miracle, right? Because it should have been trivially second order, but it's not trivially, it should have been trivially first order, but it's not trivially first order. Okay, so the strategy is the following. First, let's understand the theory of possible continuous superfluid to charge ordered Metal-insulator transition of bosons at commensurate filling, and then let's couple this theory to the spin-on Fermi surface. Okay? So that will enable us to address the question whether there's a possibility of a continuous mode transition in an electronic system at commensurate filling. There's many important couplings in this problem, even if we could understand this bit. First, there's a coupling between the boson and fermion due to the gauge fields of the slave boson decomposition. So that's the same phenomenon that exists already at zero doping, at x equals 0. Second, there's a coupling between the energy density of the bosons and the density of fermions. That's also an interaction that exists in the problem at x equals 0. There it turns out to be irrelevant. Finally, because this transition is associated with the onset of charge order out of a uniform Bose condensate, there will be critical charge order fluctuations, and likewise there will be critical nematic fluctuations. Now these will also couple to the spin-on Fermi surface, and we have to worry about the effects of the spin-on Fermi surface on those order parameters as well. Okay? But you know, if this theory is tractable, then and there is a continuous mode transition, the corresponding critical fixed point will have a critical Fermi surface, but no sharp Landau quasi-particles. It will have critical charge order correlations. It will have critical nematic correlations, and it's at finite density. Right? So it's a nice example of an interesting strange metal fixed point, which one may learn something from, right? For the cuprates. It's an insulator, but so long as you're close to that fixed point on the metallic side, you would expect to see its effects of the critical fixed point. Right. So the question you could ask in the cuprates is at 20% or 25% doping, you know, are you coming close? Is the physics in that regime controlled by proximity? It's metallic, but is it controlled by proximity to a charge-ordered insulator, to an exotic charge-ordered Morton insulator, right, at finite density? I don't know, right? And most likely not. But you know, it's good to build examples and good to build intuition about exotic states at non-zero density. Okay, so that's what I would like to do. So let me start by discussing some simple things. So if the superfluid to charge ordered insulator transition of bosons is second order, then it will be characterized by some bunch of critical exponents. There will be a correlation length exponent nu, as usual. There will be a dynamical critical exponent z. Now, we know enough about this transition that we can reasonably expect that z is equal to 1 and that it's some relativistic quantum critical fixed point. There will be an anomalous dimension eta for the boson field. There will be an anomalous dimension eta for the charge order fluctuations, which in the deconfined critical language, these are the VBS fluctuations. There will be an anomalous dimension eta nematic for the nematic order, which is also onsetting at this critical point. And it's easy to derive criteria for when the coupling to the spin-ons does not change the bosonic criticality, just as it did not change the bosonic criticality at zero doping. Right? So at zero doping, what happened was that all the fluctuation in the spin sector dynamically decoupled from the charge sector. Right? The charge sector affected the spin sector did not affect the charge sector. Right? So the first question we want to ask is, will that phenomenon of the charge sector inheriting the same transition as in the pure boson system, when will that happen? Okay? Because if that happens, then life is really simple and we can work everything out. So the gauge field coupling is similar to what happens at x equals 0. So the boson sector is described by relativistic critical theory, because the Landau damping of the gauge field will still continue from the spin-on Fermi surface. And so long as the charge sector is described by a relativistic CFT, the arguments that I gave before will continue to hold, and particularly the gauge field will decouple from the boson, but will be affected by it. Okay? Now the coupling of the boson energy density to the Fermi surface will lead to an interaction of this term, to a damping of the boson energy fluctuations. And this is known to be relevant if nu is bigger than 2/3. I think it goes back to, again, some ancient paper of Subir and Morinari from, I don't know, 2002, something like that, prehistoric times. Now the charge order fluctuations, in the language of this putative deconfined criticality associated with the boson sector, the charge ordering is what we call a monopole operator. It's of the kind that Ribu was calculating in great detail. It's an instanton for the appropriate gauge field. So usually at the deconfined critical point, those sort of single monopole operators not allowed. Ribu mentioned that only quadruple monopoles allowed at half filling at q equals 2. But here, there's a term that's linear in this charge order parameter, in this charge CDW order parameter that's allowed. It's a term that couples to a bilinear of the fermions. Okay? And in fact, it's a standard coupling that's kept in theories of conventional phase transitions, the so-called Hertz-type theories associated with the onset of charge order in a Fermi liquid metal. Okay? Now, that coupling will lead, so the fermions will then lead to a Landau damping of these charge order fluctuations, which takes this form. And you can ask when this is irrelevant at the bosonic fixed point, and it turns out that it's irrelevant if eta charge order is bigger than 1. And similarly, the nematic fluctuations, which sit at q equals 0, they will couple to all points of the spin-on Fermi surface. And so their damping will be stronger. And for them to be relevant to the bosonic critical point, you need this eta exponent for the nematic fluctuations to be bigger than 2. So we have a set of criteria for when the spin sector fluctuations, for when the F sector fluctuations decouple dynamically from the boson fluctuations. Okay? So an effective critical action then, if will take this form, where S of B is this possible non-Landau critical theory for the superfluid to charge ordered insulator transition of bosons at filling 1 over Q. And this is the standard spin-on Fermi surface coupled to this Z equals 2 Landau damped gauge fields. For this kind of story to work, the criterion is that the boson sector needs to be relativistic with exponents that satisfy these inequalities. If these inequalities are not satisfied, then the critical theory will be more complicated, and we have to do a hell of a lot more work to figure out how this transition goes. Okay. So let me tell you what's known about the superfluid insulator transition of bosons at commensurate filling, 1 over Q. This will mostly be a review of previous work, and we'll actually see that not much is known. Okay? So it turns out that the right way to think about this problem is using a dual vortex description, not work with the bosons directly, but work with vortices in the boson phase. So many years back at Q equals 2, we worked this out with some struggle. And then for general Q, there's a beautiful paper by many people in the room, Krishnendu somewhere in the room perhaps, and Subir, which generalized this to arbitrary Q. So that's the only work that basically exists. Right? So it turns out that this dual description in terms of vortices is very convenient to incorporate the Berry phase effects of the lattice filling. Okay? Now I shouldn't be explaining duality here, but because Lasik already explained it, and besides I see Chandan Dasgupta sitting in the audience. So Chandan invented the duality. And that was really in prehistoric times. So you see Dasgupta, Halperin in 1980, before I bet any of the students in the room were born. So let me very quickly describe this and then I'll stop. So for conventional 2D bosons, there's this dual description in terms of vortices, where this field phi is the vortex in the boson phase. The boson density, the boson current is described, the boson current is conserved, right? D mu, J mu is 0. So you can solve that equation by writing J mu as the curl of some vector field A. And to incorporate that this is a vortex, you just couple this boson minimally to A mu. And this capital A mu is an external probe gauge field that couples the boson current. So in this dual description, the boson superfluid is described as an insulator of vortices, and the Mott insulator is described as a condensate of vortices. Okay? So the advantage of this dual description, as I said, is that it makes it very easy to incorporate the lattice effects of fractional filling. So if the bosons are at filling 1 over Q, then it means since that the vortices, as they move around on the dual lattice, will see this average filling of the boson as an average flux of 2 pi over Q. Now, what this means, this non-zero flux seen by the vortices, means that the realization of translation symmetry for the vortices is highly non-trivial. It's realized projectively. You know, in the magnetic field translations, Tx and Ty don't commute with each other. So there's something called magnetic translations. And if the flux is 2 pi over Q, what that implies is that the vortex band structure is Q-fold degenerate. Okay? So then there's a natural dual Landau-Ginzburg theory where you take into account the fractional filling by incorporating it as a Q4 multiplication of the number of vortex species and write down a theory of Q species of vortices all coupled to the same non-compact U1 gauge field. Okay? So that's the essential idea of the Balance et al. Paper worked out in gory detail at some general filling 1 over Q. So, sorry? Equations. So what they propose based on this line of attack is a dual field theory. And we don't know if this dual field theory has a critical point. So that's why I say it's possibly critical. But at least we have a field theory. Right? So that's the most that analytic work can do in this field. Okay? And this dual field theory consists of Q species of these vortex fields that are coupled minimally to a fluctuating U1 gauge field. And then there's a quartic potential, which is very, very complicated. Okay? So this quartic potential is written in terms of these operators, rho and m. So phi n, phi m are the different vortex species, and this combination is gauge invariant. So it's a physical operator. And this combination is transforms non-trivially under physical lattice symmetries and lattice translation, lattice rotation. So these are precisely the physical charge ordering order parameters. Okay? So this is the theory that one needs to solve to figure out if there's a critical point and then evaluate whether the experiments satisfy the inequalities that I need them to satisfy if this theory is to decouple from the fermion sector. So the current status is that unfortunately there seems to be, as far as I can tell, it's been 10 years since this work, which I've of course been very, very familiar with. There don't seem to be any sensible analytic ways of deciding whether such a non-Landau critical point exists or not for Q bigger than 2. And Ribu is here with his powerful technology that he's been developing for the last many years. It seems to me that there may be some hope for making progress on this kind of question by studying these kinds of field theories numerically. And the way to do that may be to start with what Ribu already has, an SUQ spin system, and then put in the right kind of anisotropy to mimic this field theory. Okay? Maybe what it needs is a younger version of Ribu. The next generation to boldly go where Ribu has been afraid to tread. Right? But I think it's worth doing, if not for the purposes of what I've been describing, just as as an exercise in understanding quantum criticality in general. Right? Can the superfluid mode-insulator transition of bosons at filling quarter on a square lattice, can that be second order? Right? It's a non-Landau quantum critical point. Anyway, so that's where I am. I'm stuck because I don't know how to go beyond this. I can't do anything analytic until Ribu or his future descendants do something numerically. We have no way of evaluating whether these, of bootstrapping from this to the fermion system and saying anything. Right? Anyway, so let me just stop here. So let me summarize. So the quantum spin liquids provide an opportunity for progress on these classic old problems, the mode transition and other metal-insulator transitions. So at half filling in the context of the organics, the theory I think is in pretty good shape. And there's many predictions for experiment, which people are working on, experimenters are working on right now. There's also similar predictions. The theory is also tractable in 3 dimensions. It's appropriate for this hyper-Kagame iridate. And there's a prediction of resistivity peak. I don't know that there's any experiments trying to look for that. Maybe Yogesh can be motivated to do something. For other commensurate filling, I can derive criteria for when a certain kind of continuous mode transition may occur. But beyond that, I've not been able to go. I've not discussed this in this talk, but since Arindam gave this very nice talk today, I should say that it's sort of interesting in light of all the progress and understanding this kind of mode transition to go back to disordered systems and at least pose some questions. And there's a particularly interesting question that, as far as I know, has never been studied experimentally. What the experiments on the spin liquid organics show is that the electrical mode transition and the thermal mode transition don't have to occur at the same pressure. Okay? So it's natural to then ask whether in doped semiconductors, where the electrical and thermal metal-insulator transitions occur simultaneously. Okay? I don't think empirically that this has ever been studied. So anyway, so let me stop here and thank you all for listening to me. Yeah.
So the last point, Senthil, on this, on your, let's go back to x equals 0.
Yeah.
So the spin-on still has a Fermi surface because you are spin liquid.
Right.
And so the thermal conductivity should go smoothly across there?
Yeah, that's right, yeah. Though, yeah, the thermal conductivity will evolve smoothly, though if you think about this seriously, which we did in this paper we wrote about 2.5 years back, if the thermal metal-insulator transition is separated from the electrical metal-insulator transition, then it requires that the residual electrical conductivity jump across the electrical mode transition, so that there be a jump. That's assuming, that's making further assumptions. It assumes that it's a Fermi liquid all the way up to the metal-insulator transition, which mainly that the Wiedemann-Franz law is satisfied all the way up to the metal-insulator transition. Now that itself has never been checked experimentally. There's no, again, as far as I know, maybe TVR knows, but there's no experiment, scrutinizing the validity of Wiedemann-Franz all the way up to the metal-insulator transition in a highly disordered semiconductor. And theoretically, people went back and forth on whether Wiedemann-Franz should hold in a strongly disordered Fermi liquid or not for a long time. Right? And when the dust settles, it looks as though it should hold. But despite all this theoretical controversy, there's been no experiment.
Yes, a small question. See, it seems the validity of Luttinger theorem is important to your setting up this effective field theory, that on the Fermi liquid side, there is this actual fermion, whereas on the Mott side, there is not a real quasi-particle, but the area conserving contour in K-space survives. And
as a ghost Fermi surface.
That's right. So there is an associated ghost fermion, but so the contour is important, that there is a K-space contour. Now the question is, in these effective field theories that you have developed to describe the continuous metal-insulator transition across critical point, can one systematically show, or you have shown, or that indeed the Luttinger theorem is valid in the effective theory, in terms of these?
You mean in the Fermi liquid phase, or
no?
In either phase? Yeah. In this framework, the Luttinger theorem is definitely.
Is it obvious? I mean, I don't know.
It's obvious. There's no mechanism for violating Luttinger anyway here.
So my question was, if you were to calculate, for example, Green's function for the physical electron operator using these pseudo operators F and B's, and then actually see if it is indeed true or not.
Right. So Luttinger's theorem is a statement about the Fermi liquid, right? So in the Fermi liquid, it's absolutely true that the physical electron Green's function will have a pole at the Fermi surface that satisfies Luttinger's theorem. You could ask a more delicate question, whether the spin-on Fermi surface satisfies Luttinger's theorem. Okay, but even there, it's known that if despite all this coupling to the gauge field and so on, it satisfies Luttinger's theorem.
Okay.
Yeah.
Yeah, I have a very short question actually. What's the order of the transition in the disordered limit of the Mott transition?
Of the metal-insulator transition? So the postulated exotic phase transition that we described is second order. Despite that, the electrical conductivity jumps.
Sorry, so electrical conductivity gives a discontinuous jump.
Despite that, the transition is actually second order.
Okay. Is that because of the fact that you have got spin-ons which is making it?
Sorry?
I mean, I don't understand. So is that because the charge localization is a first order, but the spin?
No. The charge localization is also second order, even though the resistivity jumps. There's a, for instance, the superfluid insulator transition of bosons in 2 dimensions. The conductivity jumps as you go through the transition, right? It's infinity in the superfluid, It's 0 in the insulator, but at the critical point, it has a non-zero constant value. Right? So that's bizarre, right? There's a jump of the conductivity.
Okay.
But it's still a second order transition. Right? So it's the same, it inherits that same kind of thing here.
So using electrical measurements, it's impossible to make out whether it's a first or a second.
You can make out, if you could measure everything, you can make out that it's second order transition. For instance, if you go all the way back, yeah, you take this, you subtract out the metallic resistivity, and you look at the change. You subtract off this background, right? And then after you subtract this background, you look at the rest of the data. You should be able to scale it in this form. Right? So that's a purely transport experiment, electrical transport experiment. That's also true, but here it's a particular kind of second order phase transition. Right? Yeah, so that's the other comment, that if you're in 2 dimensions, with disorder, you'll always be, there's general results that tell you that you can't have a first order transition. Yeah. Exactly, yeah. But even in the clean limit, so this is a statement about the clean limit, where disorder is only important in giving you some residual resistivity. But even here, even though there's a jump of the residual resistivity, it's second order, and you can tell that it's second order through electrical transport experiments.
Is it true at all orders that your gauge fluctuation is actually decoupled?
Yeah, yeah. That is true.
Any other questions? If not, oh, sorry.
Now that all the important questions are done, I want to ask something completely different. So whenever I have seen the cuprate phase diagram, there's this gap between when the antiferromagnet goes away and the superconductivity comes up. And if you go to the old papers, you see that there is a spin glass phase there.
Right.
So is that not connected to anything at all, or why is that never mentioned?
Yeah, okay, so you can mention it. The problem, of course, my phase diagram was schematic, right?
Yeah.
No, it's a question of what you're interested in, right?
No, does it?
No, so there is a tiny, empirically, there's a tiny blip of spin glass here.
Yes.
Now, for most of the issues in the cuprates, this tiny blip of spin glass, one would imagine, is not a very important phenomenon.
Yes.
It's not tiny for lanthanum materials.
I see.
No, for YBCO, the latest thing, it's actually, I think it may not be an ordinary spin glass. It may be what we call a spin density wave glass.
But yeah, is it understood because you're not disordering the copper lattice at all? Why is the spin glass coming there? What is the frustrating interactions then?
Oh, there's some disorder in the system, and if it's really this lanthanum, if it's really the stripe type, Xantiphase stripe type thing, it's very, very sensitive disorder because it's breaking translation symmetry.
Okay.
Right? So the spin glass is there in some cuprates, but no one expects that the spin glass is playing a fundamental role in any of these other phenomena. So you could be interested in the spin glass. Now, if you were interested in the spin glass for its own sake,
no, I'll tell
cuprate
you
is the
why.
best system to study spin glass.
No, I'll tell you why I'm saying this.
Yeah.
A lot of people after the cuprates tried to like dope mod insulators to get to superconductivity.
Yes.
And as soon as they see a spin glass, they say, well, it won't work. But if the spin glass was shown here, then there would still be hope.
It depends. If you see a spin glass at 300 Kelvin, then you worry. If you see it at
sure. Okay. Yeah.
Any other questions? Well, if not, let's thank Senthil again, not just for this talk, but for all 3 lectures that he's given. And we'll meet again tomorrow at 9 o'clock for the last day of the meeting. We have talks only in the morning session by Subir Sachdev, Brijesh Kumar, and Anders Sandvik. almost definitely not be able to make it exactly by 9. So you
I'll
will
be
have-
there.
Okay.
9 I'll
And
be
we
there.
need a
Session
second
chair.
chair.
Brijesh.
Brijesh is
Yeah.
just.
Is it okay if I speak to you?